Hello and welcome back everyone, this is Sancarn again here, bringing you another video, and today we are going to make a raging tornado. First we are going to explore briefly how we are going to make the tornado, and then I shall take you step by step through the problems we face in creating it. So first of all, what are the characteristics of a tornado which we want to recreate? The first thing we want to do is make it have a spiraling motion and at the same time be destructive. For this we can use TNT spawning in a circle, where each TNT has a velocity towards the center of the circle. If we repeatedly spawn this TNT and let it fall, it will give the effect of a spiraling motion. The second characteristic we want to recreate is the motion of a tornado. If you follow the center of a tornado, it has a locally random path. However, it has a globally determined path. It is a myth that tornadoes generally travel northwest. However, we are going to assume that this myth is correct for our build to make it simpler. To deal with the second characteristic, we are going to use a squid named Raging Tornado. The squid will represent the center of the tornado. To prevent the squid from falling to the ground, we will have a barrier block underneath it. For testing purposes, we will use bedrock. To move the squid, we will use the set block command to first place a block in the direction of movement. Then we will teleport the squid and proceed to delete the block it came from. To place and replace the blocks, we use the execute command on the squid named Raging Tornado with an embedded set block command. This is how it looks in practice. To produce the locally random path, we use a randomizer. This randomizer can be biased by increasing the number of non-stacking or stacking items in the dropper. Because we wish to make the tornado have a globally determined path by having it head northwest, we will make it biased towards the northern and western directions. Altogether, we have a clock which leads into a randomizer, which decides whether or not the tornado moves. This line then leads into two more randomizers. One that decides whether the tornado goes in the positive or negative X direction, and another that decides whether the tornado goes in the positive or negative Z direction. Now that we have completed the movement system for our tornado, we need to create the spiraling vortex of TNT. For this, we wish to spawn ignited TNT entities around our squid, Raging Tornado, and give them a velocity towards the center of the circle. We will use the execute command with an embedded summon command with relative coordinates to accomplish this. We wish for the radius of the tornado to be 15 blocks, and by testing we can see that at x equals 15, we will need a velocity of roughly Vx equals minus 0.4 meters per second. We also wish to create roughly 22 TNT entities per cycle. This is enough information we need, with a bit of mathematical calculation, to find the relative coordinates for the summon command. To do this, we start with the formula for a circle. X squared plus y squared equals r squared. Sadly, however, this isn't that useful. We would prefer a formula which uses the radius r and the angle phi. So let's try and call x equals a cos phi and y equals b sin phi. We can see from this that a squared cos squared phi plus b squared sin squared phi has to equal r squared from the formula of the circle. A trigonometric identity used a lot in mathematics is cos squared phi plus sin squared phi equals 1. If we sub this entity into the right hand side of the equation, we get a squared cos squared phi plus b squared sine squared phi equals r squared bracket cos squared phi plus sine squared phi bracket. By expanding the brackets, we get a squared cos squared phi plus b squared sine squared phi equals r squared cos squared phi plus r squared sine squared phi. Now let's just take the algebra to the side and compare the two sides of the equation with each other. If we take the coefficients of the cos squared phi's on both sides, we can see that a squared equals r squared. Whereas, if we take the coefficients of the sine squared phi's on both sides, we can see that b squared equals r squared. Ultimately, we see that a equals b equals r. Thus, x equals r cos phi and y equals r sine phi. These are called the polar coordinate representation of a circle. Phi here is between 0 and 2 pi. Now, with this in mind, let's let phi equals 2n pi over k, where k is a constant integer and n is the set of all integers from 1 to k. Let's take an example, because otherwise this is going to get theoretical and complicated. Let k equal 3. This gives our general equation for phi equal to 2 pi over 3 times by n. When n equals 1, phi 1 equals 2 pi over 3. When n equals 2, phi 2 equals 4 pi over 3. When n equals 3, phi 3 equals 2 pi. Using our formulas for x and z, we find our points. Point 1 is where x1 equals minus 0.5r and z1 equals 0.9r. Point 2 is where x2 equals minus 0.5r and z2 equals minus 0.9r. And point 3 is where x3 equals r and z3 equals 0. So for k equals 3, we have 1, 2, 3 coordinates. So from our example, we can see that if we choose k correctly, we can change the number of TNT around the circle. As mentioned before, we want 22 TNT around our circle. Therefore, we want k to be equal to 22. So let's get into Microsoft Excel and work out the relative coordinates we need. First, we set up n from 1 to k, which is 22 in this case. Second, we want to set up phi, and for this we need the constant pi. We then literally just specify the formula in terms of Excel cells. For cells which remain fixed in the same position, we can use the $sign. After finishing the formula for one cell, we copy it down to all other cells. Third, we find the x and z for specified phi. Since these two values are very close to 0, we are just going to approximate them to 0. Finally, we are going to format these cells so they give their solutions to 3 decimal places. We can use exactly the same method to calculate the velocities we need to use, but instead we replace r for the velocity vx minus 0.4 mentioned earlier in the video. After this, it's just a case of copying the x, z, vx and vz coordinates to the execute command in a line of command blocks. To make these command blocks go one after another, I am using the set block command. Every time the command is run, it will produce a spiral of TNT. To make it look like a continuous spiral, we clock it, spawning redstone blocks inside the command block chain. So finally, we have created the main characteristics of our tornado. Now all we need is a way to spawn it, and a way to delete it. To spawn a tornado, we are going to use a sheep called spawn tornado. When the sheep is spawned, this command block places invisibility on the sheep. When the command is successful, it turns this comparator on. This triggers another set of command blocks, creates a block 20 blocks above the sheep, spawns a squid, whose name is Raging Tornado, 22 blocks above the sheep, and sets mob loot to false. We then kill the sheep called Spawn Tornado, and give the squid named Raging Tornado an invisibility potion effect. Finally, we set the mob loot back to true. The system then spawns a falling sand entity, which breaks on a pressure plate. The sand item entity then falls on the pressure plate, powering it. After 5 minutes, the item will despawn, activating the last set of commands. These commands firstly delete the block underneath the squid, named Raging Tornado, and then proceeds to teleport the squid below the bedrock so it will be deleted by the void. So, all in all, this is our contraption. We have the starting mechanism over here, in the middle we have the TNT spawning, and on the right hand side we have the moving mechanism. But the question is, how does it all look? Sadly, my computer couldn't cope with this much TNT, but fortunately Cellulance was a great help and recorded it in use for me. There are probably a few more tweaks here and there that need to be done, but unfortunately that's all I have time for in this video, so I guess I'll see you again in the next video.